Let us now discuss some improvements that can be made to the series regulator circuit so that the precision of the regulation can be improved. So first, let me take up the case of RZ and then next the case of RB. See, through both these components, the current that is supposed to flow through are supposed to be constant for effective regulation. However, Vi here is unregulated and therefore it is a varying voltage. So therefore, we cannot strictly say that the currents that are flowing through RZ and RB are constant. Now let us take the case of RZ. If we shift this RZ from here to here, V0 is a regulated voltage node point. Therefore, if we shift this to here, the current through RZ can be effectively said to be constant. So let me remove this RZ from there and then reconnect it here in this fashion, RZ, and you see that here the voltage is V0 and V0 is a regulated voltage and therefore it is constant and fixed. Therefore the current through RZ is fixed, and as a consequence the regulation, the V0 reference is much more stable in this arrangement. However, the question arises, will this arrangement allow startup? Means at the time of starting, the output voltage is 0. What will happen? At the time of starting, V0 is 0. Zener breakdown has not happened. Here also it is 0, AV0. Q2 is out of the picture, it is off. So all the input bias currents through RB flows through the base of Q1 and tries to turn that on. And the voltage starts getting developed here. Once the voltage starts getting developed here, Zener comes into the picture, V0 ref is set, and the output voltage will track this V0 ref. So therefore, we can say that this arrangement will allow startup and also improve regulation by virtue of a more constant current flowing through RZ. Let us discuss another important improvement in the series regulator circuit to improve the regulation precision, and that is in this current IRB. We saw earlier that for effective regulation, IRB is supposed to be constant, and the IRB splits up into IB1, base current of Q1, and IC2, collector current of Q2. IC2 and IB1, the base current of Q1 and collector current of Q2, they commutate amongst themselves so as to achieve effective regulation of output voltage V0. Now we see here that Vi is unregulated voltage, which means that it can fluctuate. If it can fluctuate, the voltage here, IRB being given by the voltage here Vi minus V0 minus VB1 divided by RB. V0 and VB1 are constants. However, Vi is not actually constant because the input voltage is unregulated, so which means it can vary. So as a consequence, IRB is not strictly a constant current value which is flowing through RB, and therefore this is a serious cause for deteriorated regulation. So how do we solve this? One way to solve this is to remove this RB and put in there a current source like this, and if you put in a current source, irrespective of variations in Vi, the current here will be constant and thereby the regulation will be very precise for the circuit for any variation in load and line. We also know that a current regulator can be made using the Zener shunt regulator. Let us make that and introduce at this point. So let us make some space. Let me put in the current regulator circuit, a resistance, a PNP, and the output of that connected here, and then I have a Zener and the resistance here. So look at this. This is Zener, which is giving a constant voltage that is applying between these 2 points I am showing. VB is constant, so essentially Vz minus VB will come across this resistance, and this resistance being fixed, Vz minus VBE by this resistance will be a constant current flowing through the emitter, and thereby a current which is alpha times the emitter will come into the collector and then flow in here, and the collector current will be essentially constant irrespective of the variations in Vi here. And now that is a crucial improvement where this current being constant, the regulation will be very, very precise and effective. Now let me discuss another important, significant improvement to the series regulator circuit. Here I am talking of replacing this transistor Q2 itself. The transistor Q2 is supposed to provide amplification, current gain, and also a high input impedance as seen from this side. The same thing can be provided in a much better way by using an op-amp, which is supposed to have an infinite gain and almost infinite input impedance. So let us try to use an op-amp and improve the regulation performance of the circuit much better. So remove this portion. This portion which is providing the V0 reference is still retained, and this attenuator which is actually tapping off the output providing the feedback AV0 is also retained. The transistor portion will be replaced with an op-amp. So let me have a drive resistor to drive IB into the Q1 base, and the IB drive is being obtained from the output of an op-amp like this. So op-amp is a 3-terminal device. There are 2 terminals for power supply. Let us take the power supply for the op-amp from the unregulated voltage itself, and I will give the feedback tap-off point to the minus terminal of the op-amp and the voltage V0 reference to this point. Observe that the op-amp has infinite input impedance, which means that the V plus voltage and the V minus voltage are almost same, meaning that there is a virtual ground in the op-amp, even though there is no current flowing through the high input impedance. This means that whatever value of V0 reference you are setting here, the AV0 will track this V0 reference almost exactly. Further, there is almost zero current flowing into V plus, and therefore the Zener and the Zener impedance, that is RZ, also doesn't cause deregulation because this is essentially a fixed value of current. Now the regulation action, how does it regulate? Now let us say, for example, this is IB1, and for example V0 increases due to some reason. The V0 may increase due to change in Vi, change in R0. So if V0 increases, then AV0 will increase, and then as a consequence AV0 which is given to the minus will be higher than, will increase more than the plus V plus terminal voltage which is being held constant. Therefore the error decreases and the output of the op-amp reduces, op-amp output reduces, and as a consequence IB1 drive will reduce, And if IB1 drive reduces, VCE will increase because the transistor Q1 is pushed more towards the cutoff, and as a consequence VCE will increase. And if VCE increases, then the outer loop Kirchhoff's loop will see to it that V0 decreases and is brought back to its original value. Now this is the regulation action, the closed loop regulation action. Likewise, even if V0 decreases, the same sort of regulation action happens. V0 decreases, AV0 decreases, error increases, IB1 increases, VC1 decreases, and therefore V0 increases and is brought back to its original state. So to this improved regulator, that is the one with the op-amp connected like this, you can improve it still further by placing the Zener such that it is tapped from the output side rather from the input side. So let us say we tap the Zener input. Instead of from Vi, you tap it from V0. V0 is regulated, and therefore this will be well regulated, absolutely stiff V0 reference, and it will be one of the most precise regulators that you can have. However, will this start up? So when you are starting up, V0 is 0, this is 0, this is 0, output of the op-amp is not defined. And it may turn on this or it may not turn on Q1, but we cannot, a designer cannot leave that one to chance. Therefore, we should ensure or guarantee turn on. So what we shall put is, we shall put a resistance division like this, and at this point I will tap off, put a diode, normal diode, and connect it there. So how does this operate? Let me take an example. Let us say we have a 5 volt Zener. So this V0 reference is 5 volts. This is A V0. Let us say this is R and R equal, which means A is 0.5 and therefore V0 will be 10 volts. So if this is 10 volts, input of course will be much greater than 10 volts. Now let me set this value, this potential division, to 4 volts. Then initially on startup 4 volts comes across at this point, and here 4 volts will be available to you if this is an ideal diode, or 4 volts minus the diode drop. Now this will act as the reference, and this will push this transistor, and the regulator will come into being, and at this point it will be 2 times 4, 8 volts. The moment this potential here crosses 5 volts and the Zener starts to go into the Zener breakdown, this will be 5 volts. The moment this is 5 volts, this diode will get reverse bias because it is 4 volts there, 5 volts here, and goes out of picture, and the Zener will set the reference and the operation will be as usual, as normal. Additionally, you can also give current limiting for this circuit also. At this point you can include a constant current limiter like this, put a resistance there, then put a BJT and connect it in this fashion. As the voltage across this resistance increases, VB will increase, and it will try to remove the drive from the base drive from this main transistor. It will divert the base drive and see that this transistor blocks a higher voltage. You can also replace this with a fold back current limiting circuit too. It will also operate equally well in this case.